In the vast and unending dark, a whisper moves, not through air, nor through silence, but through the ancient fabric of space itself. It drifts endlessly, faint as dust on a cosmic tide, carrying the first breath of everything that ever was. This signal began its journey nearly 14 billion years ago, when the newborn universe exhaled its first light, a radiance so young that time itself had barely begun to count. That light, once blinding, has faded to a cold, delicate hum, a relic of creation, stretched by expansion, softened by eternity. It fills the universe completely, a sea of invisible warmth that touches every atom, every planet, every heart that dares to listen. It is not a sound, but the closest thing the cosmos has to memory, a song from an age when matter and energy were one, when the first atoms were forming, and the universe itself was still deciding what it would become. Across billions of years, that whisper has survived the births of galaxies and the deaths of stars. It has passed through the dust of ancient worlds, through the frozen edges of intergalactic night, until it found instruments built by fragile hands on a small, blue planet, machines that could finally translate its language of light. It is the oldest message ever received, the afterglow of the Big Bang itself. Within it lies the code of creation, temperature, structure, symmetry, and the first map of cosmic order. But beneath the data, beneath the static, there is a deeper mystery still waiting to be heard. For in that whisper from the edge of time, the universe may be telling us not only how it began, but why it began at all. The story begins not in the stars, but in a field of quiet grass and rusting steel, where the sky was first measured by accident. It was 1964, and the world had not yet learned to listen to the silence between the stars. At Bell Telephone Laboratories in Holmdel, New Jersey, a great white horn antenna stood like an ear turned toward the heavens, a machine designed for earthly communication, not cosmic revelation. Arno Penzias and Robert Wilson, two radio engineers, had been tasked with refining its sensitivity for satellite experiments. They expected precision, data, perhaps a few technical frustrations. What they did not expect was a voice from the beginning of time. The anomaly appeared as a faint hiss, a low, uniform background noise that refused to vanish. It was everywhere, constant, unwavering, no matter where the horn pointed. Toward the Milky Way, the horizon, the empty void above, the hiss remained. It was as if the entire sky were whispering at once. They suspected interference. Bell Labs sat beneath the flight path of migratory pigeons, and for weeks the engineers cleaned the horn's interior, removing droppings, tightening connections, checking amplifiers. They recalibrated every component, searching for the flaw in their own craftsmanship. Yet the hiss endured, stubbornly perfect, immune to explanation. Across the river at Princeton University, a quiet revolution in thought was already unfolding. Physicists Robert Dicke and Jim Peebles were wrestling with a cosmic question. If the universe began with an immense explosion, a Big Bang, then its early fire should have left behind a faint glow, a residue of light that, cooled by cosmic expansion, would now fill all of space. They called it relic radiation, a ghost of creation's first heat, predicted to be just a few degrees above absolute zero. But theory without detection was nothing. They needed to find it, and did not yet know that two engineers had already stumbled upon it by chance. One summer evening, Penzias and Wilson contacted Bernard Burke, a radio astronomer at MIT, describing the mysterious signal that haunted their data. Burke, intrigued, mentioned it to Dick. When Dicker heard the account, he paused. Then, turning to his colleagues, he uttered the words that would echo through the history of science. "Well, boys, we've been scooped." In that moment, two separate paths, one born of curiosity, the other of precision, converged into one of the most profound discoveries in cosmology. The hiss was no noise at all. It was the faint afterglow of the Big Bang, the cosmic microwave background, the first light to ever escape into space, now stretched thin across 13.8 billion years of expansion. When the data was published in the Astrophysical Journal Letters in 1965, the implications shook the foundations of modern physics. The steady-state model, which had imagined the universe as eternal and unchanging, began to crumble. The cosmos, it turned out, had a beginning, a violent, radiant birth that left its fingerprint on the very sky. This light was not visible to human eyes, but its presence was everywhere. Its temperature was uniform, about 2.7 kelvins, just above the silence of absolute zero. It filled every corner of the universe, an ocean of microwaves so faint that only the most sensitive instruments could hear it. Yet in its quiet persistence, it spoke volumes. It told of an age when matter and radiation were one, when atoms had not yet formed, when the cosmos itself was still opaque, its light trapped within a dense fog of plasma. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons to bind to protons, forming the first hydrogen atoms. Light, once imprisoned, was finally free to travel. That ancient flash, the very moment when darkness became transparent, is what Penzias and Wilson had captured unknowingly in the static of their antenna. The discovery did not just confirm the Big Bang, it opened an entirely new way to see the universe, not through the scattered light of stars, but through the preserved memory of creation's first illumination. It was a map, hidden in radiation, waiting to be decoded. For cosmologists, this was more than a technical achievement. It was revelation. The universe had left a message written in light, and that message was still arriving, not once, but continuously, in every direction, every second, on every wavelength between 1 and 10 millimeters. The cosmos itself had become a storyteller, speaking across time with a voice older than galaxies. In laboratories and observatories, this realization ignited a quiet awe. Scientists understood that the radiation was ancient beyond comprehension, that each photon had traveled unbroken since the dawn of light. Every measurement of it was a direct conversation with the early universe. In this sense, the Horn antenna at Bell Labs became not just an instrument, but a bridge, a conduit between modern intelligence and primordial time. The image of Penzias and Wilson standing beneath their antenna now feels symbolic. Two human figures dwarfed by a structure that itself is dwarfed by the endless sky. They were not astronomers by trade, yet their accidental encounter with cosmic radiation transformed the field forever. Their work earned them the Nobel Prize in Physics in 1978, but the true reward lay deeper. The discovery that the universe still carries its own echo, and that human ingenuity had finally learned how to listen. As the years passed, the signal they found would grow more than a curiosity. It would become a cornerstone of cosmology, a test for every theory of how the universe began and evolved. Yet even at its first detection, it carried a poetic weight. This was the light of the beginning, stretched, cooled, nearly lost, and yet enduring. It was proof that nothing in the universe truly disappears. Everything leaves a trace. The radiation that once burned with the heat of trillions of suns now shimmers at the cold edge of perception. It is everywhere, woven into the fabric of space, passing through walls, through air, through every living thing. It is, in a sense, the oldest light we will ever see, the light that never forgot. On that quiet day in 1964, as two engineers puzzled over a stubborn hiss, the universe revealed that it had been speaking all along. What they found was not interference, but continuity, the cosmic memory of existence itself. From that moment forward, the night sky would never again be empty. It would be known as a canvas filled not only with stars, but with the faint, endless afterglow of creation, the whisper that began it all and never ceased to travel. When the first light was heard, not seen, the world of science stood still. A faint hum, a whisper of microwaves spread evenly across the sky, became the spark that shattered the last illusion of an eternal universe. What began as a stubborn hiss on a radio receiver now stood as the oldest evidence of creation itself. For the first time, humanity had not just imagined the beginning, it had measured it. For decades, two rival visions of the cosmos had divided science. On one side stood the steady-state theory, defended by men like Fred Hoyle and Thomas Gold. A vision of a universe without beginning or end, forever expanding but eternally replenished with new matter. An infinite, self-renewing stage where galaxies drifted endlessly through time. On the other side, the Big Bang model, born from Einstein's equations and championed by Georges Lemaitre and George Gamow, told a more unsettling story. That all of space and time had once been compressed into a single, incandescent seed of unimaginable density, that the cosmos had erupted from that point and had been cooling ever since. For years, both models had survived side by side, neither proven, neither disproven, until the signal arrived. The cosmic microwave background, this faint, omnipresent glow, could not be explained by the steady state. It was not a phenomenon of stars, nor dust, nor galaxies. It was everywhere all at once and with the same temperature, about 2.7 kelvins. The light did not come from any direction. It was every direction. It was the echo of an age when the universe was a furnace, 3,000 degrees hot and filled with a glowing plasma of particles and photons. The shock was not only scientific, but existential. The cosmos, once thought eternal, was revealed as a living entity, born, expanding, aging. Humanity's place within it shifted overnight. Everything, from galaxies to atoms to life itself, now had a beginning, a common origin written in radiation. In the years that followed, physicists began to treat the cosmic microwave background not as a curiosity, but as a document, a relic of the early universe, preserved in exquisite detail. It became the first photograph ever taken, not of stars or galaxies, but of existence itself, 380,000 years after its birth. At that age, the universe had just become transparent. Before that moment, light could not travel freely. It was scattered endlessly by charged particles in a thick, glowing fog. The cosmos was a sea of energy, where matter and radiation were indistinguishable, locked in equilibrium. But as expansion continued, temperatures dropped and electrons found protons, forming the first neutral atoms. The fog cleared. Photons, no longer trapped, burst outward. The first light, finally free. That light has been traveling ever since. It is still here, reaching every corner of the cosmos, stretching thinner and colder with time, its once fiery brilliance diluted into microwaves invisible to the eye. Yet every photon carries the same memory, the same ancient story frozen at the moment the universe became transparent. This revelation was more than a triumph of observation. It was a philosophical turning point. The cosmic background radiation was proof that the universe had once been smaller, denser, hotter. It confirmed that time itself had a beginning, a moment when the equations of physics were no longer abstract, but alive, blazing, expanding into everything that followed. But within the smoothness of this light, this near-perfect uniform glow, lay a paradox. The universe we see today is structured, filled with galaxies, clusters, and cosmic webs stretching across billions of light years. Yet the cosmic microwave background appeared too even, too calm. If everything began in such balance, where did the structure come from? When scientists looked closer, using ever more precise instruments, they found what the naked data had hidden. Fluctuations, minute differences in temperature, so small they were measured in millionths of a degree. These faint ripples were not errors, they were the fingerprints of creation. Each fluctuation represented a tiny imbalance in the early universe, regions slightly denser than their surroundings, where gravity could later take hold, drawing in matter, birthing stars, galaxies, and all that followed. The entire architecture of the cosmos, every supercluster, every filament of dark matter, was born from those microscopic wrinkles in the first light. In the cold language of physics, they were anisotropies, but in truth, they were the seeds of everything. The discovery of these subtle patterns came decades later, through missions like COBE and WMAP, which transformed the faint radiation into a map of the early cosmos. Yet even in the 1960s, scientists already knew what it meant. That smooth glow was not perfection, it was potential. It told them the universe was alive with structure, still unfolding the consequences of its first imbalance. The shock of the first light, therefore, was not just that the Big Bang had happened, but that it had left behind an imprint of intention, a blueprint for everything that would ever exist. The CMB became a kind of sacred text for cosmology. Every equation about the origin of matter, dark energy, and the expansion of space would be tested against it. Every theory about inflation, curvature, and cosmic fate would either align with that ancient map or be erased. But beyond the science, the emotional weight was profound. The first light revealed a universe that remembers. Every particle, every atom, every galaxy is a continuation of that first radiant moment. The same light that once filled the young cosmos still fills the night around us, passing through walls, through clouds, through flesh. It touches everything that exists, quietly connecting all of time into one continuous story. Some scientists spoke of this discovery with a reverence usually reserved for philosophy. The universe had spoken, not in metaphor, but in measurable radiation, a silent testimony from a time when nothing yet had a name. And in that signal, humanity found its origin not in myth, but in physics, not in stories told by firelight, but in the glow that once was firelight itself. In the quiet laboratories of the 20th century, the universe had revealed that its beginning was not chaos, but coherence, not silence, but music slowed to a whisper. The discovery of the cosmic microwave background was not merely the triumph of one theory over another. It was the moment the universe confirmed it had a past, a single, unfolding narrative stretching from a bright beginning to an uncertain end. And within that story, one truth emerged with clarity, both scientific and poetic. The first light was not just the universe becoming visible, it was the universe becoming aware. In the late years of the 20th century, humanity finally learned to listen more carefully to the whisper left behind by creation. What once had been a stubborn hiss caught by a radio horn at Bell Labs was about to become a window, a map drawn across the entire sky, revealing not silence, but the oldest memory of light itself. In 1989, NASA launched the Cosmic Background Explorer, known simply as COBE. It rose above Earth's atmosphere, leaving behind the fog of terrestrial interference, carrying within it a single purpose: to measure, with unprecedented precision, the faint afterglow of the Big Bang. Its detectors were designed to read temperature differences of just a few millionths of a degree, to trace not the brilliance of stars or galaxies, but the soft embers of the universe's birth. When COBE sent back its first results, the data stunned the world. The radiation that Penzias and Wilson had stumbled upon decades earlier was confirmed to follow a perfect blackbody curve, a mathematical fingerprint of a once blazing, thermal cosmos that had expanded and cooled into darkness. It was the most precise measurement of the Big Bang ever achieved, the universe's own signature written in microwaves. But it was not just the confirmation of a theory, it was the unveiling of a portrait. When scientists turned COBE's data into a visual image, the screen filled with a cosmic dawn, a smooth ocean of light, broken by faint ripples, tiny fluctuations, temperature differences as small as 30 millionths of a Kelvin. Those ripples were the seeds of everything to come: galaxies, clusters, stars, worlds. In their delicate imbalance lay the architecture of all structure, the reason the night sky is dotted with constellations and not uniform emptiness. John Mather and George Smoot, the mission's leaders, described it not as discovery, but revelation. Smoot famously said, "If you're religious, it's like seeing the face of God." It was hyperbole, perhaps, yet fitting. For in those subtle variations, humanity saw the blueprint of existence itself, a cartography of the moment the universe became transparent, when light could finally travel free. Before this time, the cosmos had been opaque, a dense plasma of particles and radiation locked together in a blinding fog. Photons scattered endlessly off free electrons, unable to escape the chaos of their birth. But around 380,000 years after the Big Bang, temperatures dropped to nearly 3,000 Kelvin, cool enough for protons and electrons to combine into neutral hydrogen. And in that instant, called recombination, the universe cleared. Light decoupled from matter and began its journey through space-time, untouched for billions of years until it reached the cold sensors of a satellite orbiting Earth. COBE's vision was only the beginning. Its resolution was crude, a pixelated glimpse of eternity, but it pointed the way for others to refine the image. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP, a spacecraft built with sharper eyes and steadier hands. It orbited the Sun, stationed far from the Earth's radio noise, and over the course of 9 years, it traced the heavens again and again, building a map of astonishing clarity. The WMAP results revealed a universe 13.8 billion years old, composed mostly of unseen forces, dark matter and dark energy. Ordinary matter, the atoms that form everything familiar, accounted for less than 5%. The rest, invisible yet dominant, shaped the evolution of all cosmic structure. What began as tiny ripples in the CMB had grown, under gravity's slow command, into vast filaments of galaxies spanning hundreds of millions of light years. The cosmic web was born from the faintest imperfections of primordial heat. Then came Planck, launched by the European Space Agency in 2009. With detectors cooled to near absolute zero, Planck delivered the most detailed portrait of the early universe ever created. It mapped the CMB across the entire sky with such precision that every pixel told a story of density and fluctuation, of geometry and fate. From Planck's vision emerged the parameters of existence. The universe was flat within 1 part in 1,000. Its expansion rate could be measured to exquisite accuracy. Its composition could be quantified. The cosmos was no longer an enigma. It was a system with measurable laws, consistent, mathematical, and vast. And yet, amid that triumph, a quiet unease grew. For in the smoothness of the light, in its near-perfect symmetry, there lingered subtle asymmetries that no equation could easily explain. Planck's data revealed slight anomalies, a cold spot in one region, unexpected alignments in another. Some cosmologists whispered of cosmic variance, others of new physics. Could the universe, so seemingly uniform, still hide echoes of something beyond our comprehension? The questions multiplied like stars. Still, the image remained one of haunting beauty. A sky filled with patches of red and blue, glowing softly in microwaves invisible to the human eye. Each hue, each flicker represented the density of ancient matter, an abstract painting rendered by physics itself. If one could stand outside time and watch those fluctuations unfold, galaxies would bloom like frost across glass, filaments of dark matter weaving a silent structure beneath them. The CMB became humanity's first true photograph of the universe, not of stars, but of their possibility. It was the fossil light of creation, stretched by cosmic expansion into microwaves, cooled to just 2.7 Kelvin above absolute zero, a relic that has been traveling, unbroken, for almost 14 billion years, still whispering the same story. This is where it began, and yet that whisper carries another truth, a poetic tragedy. For the light we see is not the present, it is memory. Every image from COBE, WMAP or Planck is a reflection of a universe long gone, a ghostly frame frozen in time. The galaxies we now see were once the ripples in that ancient glow, the light that reveals them today left when the cosmos was young. We live surrounded by echoes, and the CMB is the oldest of them all. It is strange to realize that the sky itself is a photograph of the past, unchanging, eternal, serene. A reminder that the universe we inhabit is built upon an image, upon radiation that once burned and now whispers softly in microwaves. It tells of beginnings, of expansion, of the transformation from chaos to structure, but it also tells of loss, of everything that once was, now unreachable beyond the horizon of time. Each pixel of the CMB map is both data and elegy. In it, scientists find numbers, patterns, and proof. But they also find poetry, the kind written not in words but in temperature, in frequency, in the slow hum of creation fading into quiet. And so the satellites keep watching, their instruments cold, their gaze eternal. They orbit in silence, listening to a universe that still speaks through the faintest light. For even after billions of years, the fire of the beginning has not gone out. It has only cooled, only stretched, only transformed into a map of remembrance, into a message from before there were eyes to see it, and into the soft, endless glow that bathes the cosmos still today. For a time, it seemed the universe had finally surrendered its secrets. The cosmic microwave background, this ancient sea of faint radiation, had been mapped, measured, and modeled. It appeared perfect, smooth, consistent, and predictable, a testament to the elegant symmetry of cosmic law. But as the instruments grew more sensitive, as the pixels sharpened and the data deepened, something unexpected began to whisper through the noise. Tiny irregularities, subtle asymmetries, anomalies that should not exist. The first sign came from the earliest full-sky maps of the CMB. To the naked eye, they were masterpieces of uniformity, a near-perfect portrait of the infant universe. Yet within that near perfection, scientists noticed peculiarities that would not fade under scrutiny. There was a patch, a vast cold region, colder than the models allowed, a mysterious depression in temperature, spanning hundreds of millions of light years across the sky. It became known as the cold spot. Some dismissed it as a statistical fluke, a random deviation within an otherwise flawless field. But others were less certain. Could it be evidence of something deeper, something cosmic in scale? One interpretation proposed it was caused by a massive supervoid, a region of space emptier than most, where fewer galaxies formed and light, passing through, lost a fraction of its energy due to the integrated Sachs-Wolf effect. Yet even this explanation strained credibility. The void that would be required to produce such an anomaly would have to be unimaginably vast, larger than any structure ever observed. It was as if the universe, in one direction, had been thinned out by an unseen hand. Then came a second disturbance, more subtle, but far more unsettling. When cosmologists examined the multipole alignments of temperature fluctuations, they found a strange correlation. Certain patterns in the CMB seemed to line up across vast stretches of sky, defying the principle of isotropy, the assumption that the universe should look statistically the same in every direction. This eerie pattern was given a name that mixed humor with unease: the axis of evil. To some, it was an artifact of data analysis. To others, it was an omen, a sign that the universe itself might have a preferred direction, a cosmic asymmetry that the standard model could not explain. The discovery shook cosmology's foundations. For decades, the cosmological principle had stood as an axiom that on large scales, the universe is homogeneous and isotropic, without center, without edge, without orientation. But the CMB seemed to whisper otherwise. If true, it meant that the structure of space-time itself might carry a hidden memory, a subtle fingerprint of the conditions before the Big Bang became visible. The anomalies multiplied as analyses grew more precise. Planck's 2013 and 2018 data releases confirmed not only the cold spot and the axis of evil, but also a hemispherical power asymmetry. One half of the sky appeared to contain slightly more fluctuations than the other. The difference was small, barely detectable, but statistically persistent. A cosmic imbalance written into the oldest light, as though the universe had breathed unevenly when it was born. To some, these were the inevitable quirks of randomness, the result of cosmic variance, the fact that we observe only one realization of the universe, not an ensemble. To others, they were messages from beyond the horizon. Perhaps the cold spot was not a void at all, but a bruise, an imprint left by another universe colliding with ours in the earliest moments of inflation. If the multiverse existed, if countless other cosmic bubbles expanded alongside our own, then some might have touched, leaving behind scars frozen into the microwave sky, a silent signature of contact between worlds. The idea was both exhilarating and disquieting. For the first time, cosmology brushed against the edges of metaphysics. The CMB, once a clean window into the past, had become a mirror, reflecting possibilities that defied comprehension. Was the universe truly uniform? Or did its fabric hold secret hierarchies, alignments, and memories from before space-time itself unfolded? Physicists explored theories that stretched the imagination. Some invoked topological defects, cosmic strings or textures, remnants of symmetry breaking in the early universe. Others suggested quantum fluctuations during inflation might have amplified certain modes, giving rise to the patterns now seen. A few ventured even further. Perhaps the anomalies pointed to new physics entirely, to dimensions beyond the visible cosmos, or to a cosmic field that shaped the birth of universes like waves upon a higher dimensional ocean. But amid the speculation, the data remained stubbornly ambiguous. Each new analysis confirmed the anomaly's existence, yet none could decisively explain them. The cold spot persisted, its origin unresolved. The axis of evil endured, neither fully dismissed nor embraced, and so the debate continued, not merely as a question of astrophysics, but as an existential one. Because if these patterns were real, they meant the universe was not as impartial as once believed. It meant the cosmos has memory, direction, and perhaps even intention. The symmetry that had long comforted cosmologists, the idea that the universe is simple, uniform, and knowable, would have to give way to something stranger, something textured, something alive with history. In conference halls and late-night discussions, physicists wrestled with this paradox. Were they glimpsing the limits of observation or the limits of understanding? Was the universe trying to tell a story more complex than their equations allowed? In the quiet spaces between data and doubt, a sense of awe returned. The same awe that once followed the discovery of the cosmic whisper itself. The CMB, it turned out, was not a static backdrop. It was dynamic, enigmatic, a canvas painted with both order and imperfection. Its near uniformity spoke of cosmic harmony, but its anomalies whispered of hidden dissonance, of a deeper structure veiled beneath the observable. Perhaps that is the nature of all beginnings. Perfection gives way to asymmetry. Symmetry breaks, and from that fracture comes creation. Every galaxy, every atom, every breath is the consequence of that ancient imbalance. Without it, there would be no stars to burn, no worlds to orbit them, no life to question its origin. In that sense, the universe's imperfections are not errors, they are its genesis. The cold spot, the axis, the asymmetry, they may not be flaws in the cosmic design, but fingerprints of its very formation. Each anomaly, each statistical deviation, may hold the echo of something that once was, some fleeting quantum event that sculpted the fate of everything to come. And so, scientists continue to stare into the map of the primordial fire, searching for meaning in the ripples and the cold. The questions grow darker, deeper, more human. What if the universe's symmetry is only an illusion, a story told through limited eyes? What if our cosmic horizon hides not emptiness, but the shadows of other realities? No one knows for certain. The CMB remains, as it always has been, both a revelation and a riddle, a silent field of light, older than any star, bearing patterns that speak of creation and contradiction in equal measure. In its faint irregularities lies a truth both humbling and profound, that the universe, in all its vastness, was never meant to be perfect, only real. Long before light was born, before the universe glowed with its first visible breath, there was only a fog, dense, searing, impenetrable. A plasma of charged particles, photons, and primordial chaos, locked together in an endless scattering of energy. No light could move freely then. Every photon was trapped, ricocheting through the newborn cosmos like whispers colliding in a storm. Only when the universe cooled, 380,000 years after its birth, did that fog finally lift. Electrons bound themselves to protons, atoms formed, and the first light escaped. That ancient light became the cosmic microwave background, the surface of last scattering, the first visible echo of creation. For decades, it was believed to be the ultimate horizon of observation, the oldest signal the universe would ever allow. But now, physicists ask a deeper question. If this is only the first light, what came before light itself? The search for the signal behind the signal begins not with brightness, but with silence. For beyond the CMB lies an era the universe keeps hidden, a time before transparency, before the laws of light could even apply. To reach it requires listening to the faintest traces, the most delicate fingerprints ever imprinted on space-time. Scientists believe that long before the CMB, the universe sang a different kind of music, one composed not of photons, but of neutrinos, hydrogen, and gravitational waves. Each of these carries a secret older than light, and together they form a layered archaeology of existence. The first of these relics, the cosmic neutrino background, predates the CMB by almost a second. In cosmic terms, a heartbeat, born when the universe was less than 1 second old. These ghostly particles flooded space in unimaginable numbers, each moving almost at the speed of light. Unlike photons, they could pass through the primordial fog unhindered, escaping long before light was freed. Even now, they drift through galaxies, through planets, through human bodies by the trillions every second, untouched and unseen. Detecting them, however, remains one of science's most unattainable dreams. The neutrino's energy today is so faint, a mere fraction of an electron volt, that they blur into the quantum fabric itself. Instruments like Katrin and proposed observatories such as Ptolemy are attempting to catch their subtle signatures, but the odds are nearly impossible. Still, to find them would be to touch the universe's first breath, the moment when temperature and density still trembled at the edge of physics itself. If neutrinos whisper of the first second, then the next voice is deeper still. The 21-centimeter hydrogen line, the signal of atoms in darkness. After the light of the CMB faded and before the first stars ignited, the universe entered an age of silence, the cosmic dark ages. Hydrogen filled everything, neutral and cold, absorbing and re-emitting faint radio waves at a wavelength of 21 centimeters. This was the language of the cosmos in its adolescence, invisible to the eye, yet glowing faintly across the fabric of time. Detecting it is like trying to hear a snowflake fall during a thunderstorm. The modern universe is saturated with radio noise, from galaxies, from satellites, from Earth itself, and yet, from remote deserts and frozen plateaus, astronomers build machines designed to listen beneath that chaos. Experiments like PAPER, the precision array for probing the epoch of Ryanization, and EDGES, experiment to detect the global EOR signature, reach into the void, tuning their antennas to frequencies so faint they could be mistaken for silence. In 2018, EDGES reported something extraordinary, a dip in the radio spectrum deeper than expected, a shadow carved into the hydrogen line at a redshift of 17. If true, it meant that the first stars were forming earlier than anticipated, their ultraviolet light already interacting with the cold hydrogen around them, but the shadow was too deep, too cold. Some suggested it hinted at an unknown force cooling the hydrogen, perhaps an interaction between ordinary matter and dark matter itself. For a fleeting moment, humanity may have glimpsed the dialogue between two unseen realms, the visible and the invisible, gravity and ghost. Then there are the ripples that predate everything, gravitational waves from the universe's earliest instant. If the CMB is the first visible light, then these waves are its shadow, imprinted upon space-time itself. They were forged in the fires of inflation, that mysterious moment when the universe expanded faster than light, stretching quantum fluctuations into vast cosmic structures. The search for these waves became one of the most ambitious quests in modern cosmology. In 2014, deep within the frozen plains of Antarctica, the BICEP 2 telescope captured what seemed to be the long-sought signal. A pattern of B-mode polarization in the CMB, a delicate swirl that might reveal the fingerprint of gravitational waves from inflation. The announcement was electrifying. Humanity may have glimpsed the trembling of space-time from the first trillionth of a second after creation, but euphoria soon gave way to doubt. A reanalysis revealed that the signal was not cosmic at all. It was dust. Microscopic grains of interstellar dust in the Milky Way had polarized the light in much the same way. The primordial whisper was drowned once more in the static of the present. Yet the failure did not diminish the wonder. Each attempt, each refinement, brought science closer to silence's edge. The instruments grew more precise, the algorithms more sensitive, the ambition more daring. Space-based observatories like LightBird and CMB-S4 now prepare to continue the search, listening not for what can be seen, but for what cannot. The goal remains unchanged, to reach the epoch before light, to glimpse the cosmic dawn that even photons never witnessed, to measure the unmeasurable, the moment when space-time itself ignited. To scientists, this pursuit is more than technical. It is spiritual in its patience and humility. They build machines to capture whispers that may never come, to measure a silence that may hold no sound. It is a testament to humanity's strange defiance, the refusal to accept that any veil is final. In their data, the universe becomes a palimpsest of creation. The CMB records the surface of the fog. The 21-centimeter line maps the darkness before dawn. The neutrino background holds the first seconds of existence. The gravitational waves, if ever found, will tell the story of the instant before time itself became measurable. Each layer recedes deeper into the beginning, like peeling back the pages of creation. And in that descent, science moves closer not only to the birth of the universe, but to the limits of knowing. For at some depth, deeper even than particles or waves, lies the horizon of meaning, the place where questions cease to yield answers, where the distinction between existence and possibility dissolves. If the CMB was the universe's first light, then what lies beyond it may never shine at all. Yet still, humanity listens. For the sound before sound, the pulse before motion, the breath before being. The quest to hear the signal behind the signal is not only a scientific endeavor, it is an act of remembrance, an attempt to trace the memory of creation itself. And somewhere, beneath the static and the silence, the universe may still be speaking, in a language older than light. In the beginning, there was smoothness, too much smoothness. The universe, as seen in the cold light of the cosmic microwave background, appears eerily even, almost perfect in its balance. Every direction, every patch of ancient radiation, carries nearly the same temperature, as though the cosmos were poured from a single quiet breath. But such perfection posed a paradox. How could regions of space so distant, separated by gulfs no light could have crossed, have ever come to agree on such sameness? How could the young universe, still hot and chaotic, have been so exquisitely uniform? It was this mystery, this improbable calm, that led physicists to imagine something even more astonishing than the Big Bang itself: inflation. Inflation is not merely an explosion, it is an instant of impossible growth, when the fabric of space-time itself surged outward at speeds faster than light, not breaking any law of physics, but stretching the very space that light moved through. In less than a trillionth of a second, a speck smaller than an atom ballooned to cosmic scale. Tiny irregularities, quantum jitters born from uncertainty itself, were pulled and frozen into vast patterns that would one day become galaxies, clusters, and the grand architecture of the universe. The smoothness of the sky became the signature of that expansion. The faint ripples within it, the seeds of every future star, became its fingerprint. From the chaos of quantum fields emerged geometry, order, and the possibility of form. Inflation transformed the raw equations of physics into the canvas of existence. Yet with it came an unsettling implication: that creation, once begun, might never have truly ended. Because if inflation could happen once, perhaps it never truly stopped. In some regions, it might have slowed, cooling enough to form matter and light, our universe. But elsewhere, it may still be expanding, endlessly, birthing new universes beyond reach, beyond comprehension. A multiverse, infinite in scale, where every possibility exists, where each bubble of space follows its own laws, its own constants, its own time. Our cosmos, then, could be nothing more than a ripple among countless seas. The theory of eternal inflation turns the word beginning into something fragile. It suggests there may have been no first dawn, only an eternal field, boiling and blooming with universes like ours, forever inflating into the dark. Physicists like Alan Guth, Andrei Linde, and Alexei Starobinsky gave shape to these ideas, not as mystics, but as mathematicians. Their equations described how a false vacuum, filled with potential energy, could decay, releasing its stored tension in a burst of expansion. This energy became the blueprint of everything, the ultimate transformation of nothing into something. But the theory carries echoes of something deeply philosophical. If quantum uncertainty can birth space and time, then perhaps existence is not a singular act, but a statistical inevitability, a cosmic fluctuation waiting to occur. And if it happened once, in one small corner of probability, why not again? Why not endlessly? The image of the early universe becomes stranger under this lens. It is not a simple explosion into emptiness. It is the surfacing of geometry from a field of infinite possibility, a quantum sea giving birth to the measurable. Within that first instant, time itself became directional. Entropy took its first step forward. The arrow of existence pointed one way, and the universe began to unfold. Yet inflation's beauty is haunted by its uncertainty. We cannot see it directly. Its traces lie buried in polarization patterns of the cosmic microwave background, in tiny spirals of light that might reveal the ghostly imprint of primordial gravitational waves. Experiments like Bicep 2 in Antarctica once claimed to have glimpsed them, a swirl in the sky that might have been the echo of the universe's first breath. But later, analyses revealed much of that signal to be dust, ancient particles in our own galaxy, masquerading as a relic of creation. The disappointment was profound, yet not final. Each false signal only sharpened humanity's patience, refining our search for the genuine. Today, observatories from the South Pole to space continue to listen. They look for the faint fingerprints of inflation, the subtle twisting of cosmic light, the delicate whisper of gravitational waves that no sound can carry. If found, these signals would not only confirm inflation, but trace the moment physics itself began to write its own laws. Beyond that, speculation stretches even further. Some theories suggest that inflationary energy could have quantum entanglements across universes, that the seeds of matter in our cosmos are entangled with seeds beyond our own. Others propose that inflation may connect with the holographic principle, where all that we see, every galaxy, every atom, is encoded on a cosmic boundary, a shadow projected from deeper dimensions. In this view, the universe becomes a self-reflecting system, a field generating observers who in turn generate meaning within it. And inflation becomes not merely a beginning, but a transition, from quantum timelessness to classical reality, from probability to perception. The question deepens. If the universe inflated from nothing, what was the nature of that nothing? Is nothingness even real, or merely a human abstraction, a name for what cannot yet be observed? Quantum field theory suggests that even the emptiest vacuum teems with activity, particles flickering into and out of existence in restless equilibrium. Perhaps the Big Bang did not come from emptiness at all, but from the instability of a quantum nothing that was never truly nothing. In that sense, creation may not be miraculous, but inevitable, a ripple in the eternal mathematics of possibility. To the human mind, this sounds paradoxical. To the universe, it may simply be the way of things. The inflationary epoch remains beyond direct sight, but its effects shape everything. It defines the horizon of the observable, the boundary between what can be measured and what forever recedes. Each new observation, each refinement of data, pushes that horizon a little farther, revealing a universe that may never truly end, yet may never fully reveal itself. In the silence between equations and observation lies a simple truth. The more precisely the cosmos is described, the deeper its mystery becomes. Inflation, the grand solution to the universe's smoothness, may itself be a doorway to infinite unknowing, an idea so vast that even the language of physics trembles to contain it. What began as a mathematical fix for a cosmic anomaly has grown into the most profound vision of reality yet imagined, a universe where every instant may give rise to new infinities, where the meaning of beginning dissolves into eternal becoming. And as the telescopes hum in the cold, listening for the earliest echoes, one question continues to flicker at the edge of understanding. If everything began in expansion, if space itself was born stretching, then perhaps the truest signal of the universe is not its light, but its endless urge to grow. The story of creation, it seems, was never about where it started, but about how it never truly ends. In the vast silence of the cosmos, humanity listens. Across deserts of ice, mountaintops above clouds, and the vacuum of orbit, instruments have been raised like ears to the sky, each one straining to catch a sound older than time itself. The universe still hums with its first echo, a faint residue of creation carried through every corner of space. But that hum is buried beneath eons of static, tangled with the noise of galaxies, dust, and human interference. To find it is to separate eternity from everything else. In this age of precision cosmology, the search continues with tools of exquisite sensitivity. Machines built not to see light, but to feel its memory. The James Webb Space Telescope, suspended beyond the moon's orbit in a gravitational still point, peers into the infrared, into the red-shifted glow of the first stars. Its mirrors, coated in gold and cooled to near absolute zero, unfold like petals toward the beginning of time. Each photon it collects has traveled for billions of years, carrying the story of hydrogen clouds collapsing into the first galaxies. But even Webb cannot reach the true dawn, the age before stars, before light itself. For that, the search turns to subtler messengers, to the whisper of the 21-centimeter hydrogen line, a frequency born when the first atoms of the universe flipped their magnetic orientation, a cosmic heartbeat from when the universe was dark, cold, and filled with only neutral hydrogen. That signal has been stretched by expansion, redshifted into radio wavelengths that now wash faintly across Earth. Detecting it means hearing the age before light, the first chapter written in darkness. In remote corners of Earth, vast radio dishes and arrays of antennas listen for that elusive note. In the frozen plateau of Antarctica, the BICEP experiments search for the subtle polarization patterns in the cosmic microwave background, the fingerprints of gravitational waves from inflation. Nearby, the South Pole Telescope scans the sky in millimeter wavelengths, mapping the temperature ripples that mark the birth of cosmic structure. Each observation digs deeper into the universe's childhood, a reconstruction of its earliest breath. Far to the north, the Simons Observatory rises in the Atacama Desert, where thin air, high altitude, and clear skies make the world itself seem closer to space. Here, mirrors and cryogenic detectors await the faintest fluctuations in cosmic polarization, Each photon that lands upon them carries the echo of a 13.8 billion-year-old event. The instruments hum quietly, shielded from heat and noise, while computers translate these invisible tremors into maps, delicate portraits of creation, pixel by pixel. But even these are preludes. The next great leap, the CMB-S4 experiment, promises to listen with 1,000 times greater sensitivity. It will deploy hundreds of thousands of superconducting sensors across the globe, uniting observatories from Chile to the South Pole in a single synchronized effort. Together, they aim to extract the universe's oldest polarization pattern, the faint curling signature left behind by primordial gravitational waves. If detected, it would be more than a scientific triumph. It would be the first direct glimpse of the universe's birth cry, a vibration of space-time itself, frozen into the cosmic fabric. Above the atmosphere, the Lightbird mission, led by JAXA with global collaboration, prepares to take its place in orbit. Its detectors will drift in silence, untroubled by Earth's interference, mapping the entire sky with clarity unattainable from below. It will join a lineage of space listeners, COBA, WMAP, and Planck, but with vision sharpened by decades of refinement. Each mission inherits the data of the last, each one peeling away another layer of cosmic fog. Together, these projects form a symphony of observation, human ingenuity tuned to the edge of what can be known. The effort is not confined to laboratories or agencies. It is global, communal, and almost spiritual in its persistence. In frozen deserts, researchers wrap themselves in layers of insulation, working beneath skies so clear that the Milky Way burns with visible texture. In mountain observatories, instruments are cooled with liquid helium, their sensors vibrating with the faint hum of cosmic photons. And in orbit, telescopes glide through the shadow and light of Earth's limb, forever watching the sky that once watched them into being. Everywhere, the same goal persists: to hear through the noise, to separate the universe's first whisper from the chorus of later creation, to listen, truly listen, to the sound of beginnings. Yet this search is more than technical. It is profoundly human. The detectors, though cold and inanimate, act as extensions of human curiosity. Each one a nerve, a sensory organ reaching into the unknown. They convert radiation into data, data into maps, and maps into meaning. Through them, humanity becomes an instrument itself, a fragile species made of stardust, straining to hear its own origin story carried on the wind of light. The challenge is immense. Cosmic signals arrive faint and corrupted, buried beneath galactic dust, atmospheric noise, and interference from Earth's own technology. Each observation must be purified through calibration, subtraction, and modeling. A single false signal can mislead a generation, as the Bicep 2 announcement once proved, when cosmic dust was mistaken for the fingerprint of inflation. In science, even silence speaks volumes. The absence of confirmation becomes its own kind of discovery, reminding humanity how thin the line is between perception and imagination. But the silence does not dissuade. If anything, it deepens the wonder. For every unanswered question, a new instrument rises. For every mystery, a new frequency is sought. The act of searching becomes its own kind of revelation, proof that curiosity itself is the universe made conscious. In this era, humanity listens not only with metal and glass, but with algorithms and quantum precision. AI-assisted telescopes now scan the heavens continuously, learning to filter cosmic signals from the noise of human civilization. Quantum detectors, cooled to temperatures colder than interstellar space, record fluctuations so faint they border on the imaginary. Each advancement sharpens the ear of civilization, allowing the faintest murmur of creation to emerge from beneath the static. What they hope to hear is not just sound, but structure, the rhythm of inflation, the tone of primordial gravitational waves, the first alignment of matter with energy. Each measurement brings the universe closer to being seen as a single unfolding composition, a cosmic symphony in which the laws of physics are both composer and performer. And perhaps, when the final map is drawn, the first echo of existence will not be a roar or a burst, but something quieter. A faint shimmer of polarization, a subtle curvature of light, a vibration of space so delicate that only the most patient instruments could detect it. The kind of signal that reminds humanity how fragile its listening has always been. In this way, the search for the first echo becomes a reflection of the species conducting it, finite beings listening for infinite beginnings. Biological eyes and digital minds turn toward the same invisible horizon. The technology may evolve, the detectors may change, but the impulse remains the same, the yearning to know where the music began. And so, the observatories hum through the night. Their mirrors gleam with frost, their sensors breathe in the radiation of the ancient sky. Each photon captured, each data point stored, carries humanity a fraction closer to understanding what it means to begin. In the static, there is order. In the noise, there is rhythm. And in that rhythm, faint, trembling, nearly lost, lies the oldest sound the universe ever made. A whisper from before light, a memory carried by darkness, and the promise that even in silence, the cosmos is still singing. In the darkness between galaxies, where light thins into near-nothingness, the universe still remembers. Not in words or matter, but in radiation. A faint, cold afterglow spread evenly across the entire sky. It is called the cosmic microwave background, but what it truly is memory. The faintest trace of the first moment, still echoing through time, woven into every atom, every breath, every thought. This light was born when the universe was young, only 380,000 years old. In that ancient epoch, matter and radiation were entangled in a searing plasma, too dense for light to travel freely. Then, as the universe cooled, electrons found protons and formed the first hydrogen atoms. The fog cleared, photons broke free, and the universe saw itself for the very first time. Those photons have been traveling ever since, stretched by expansion, cooled by time, yet unchanged in purpose. They carry with them a perfect record of what once was, the density of space, the balance of matter and energy, the rhythm of creation itself. To scientists, this radiation is data, measurable, mappable, a window into the first structures that would one day become galaxies. But to anyone listening with imagination, it is also something deeper. It is a relic of awareness, a reminder that the universe has not forgotten its own beginning, that everything, even silence, remembers. The faint hum that Penzias and Wilson once mistook for noise now stands as the most profound testimony to existence itself. Each photon that brushes against an antenna or a telescope's sensor has crossed billions of years of emptiness, never slowed, never scattered beyond recognition. It has passed through eras where stars were born and died, where galaxies collided and reformed, where life sparked and wondered. It has endured entropy and distance, and still it arrives. The light we receive today has been redshifted 1,000-fold, its energy diminished to near invisibility. Once, it glowed like the light of a star, nearly 3,000 Kelvin in temperature. Now it lingers at just 2.725 Kelvin, barely above absolute zero. Yet it persists, uniform to 1 part in 100,000, as though the cosmos itself had exhaled a sigh of perfect equilibrium. And within that perfection lie imperfections, tiny fluctuations, minute differences that seeded everything. Every star, every world, every life began as a small wrinkle in this otherwise flawless fabric. The first irregularities became the scaffolding of all, complexity. When scientists stare at the false color maps of the CMB, those blue and red patches across the sphere of the early universe, they are not just looking at temperature variations. They are looking at the origin of structure, the birthplace of all asymmetry, all existence. Without these faint disturbances, the cosmos would have remained smooth, silent, and lifeless. An eternal fog of equilibrium. It is the imperfection of the first light that allowed for creation at all. And so, the CMB becomes more than a physical relic. It becomes a mirror. In it, humanity sees not only the face of the early universe, but its own reflection, a record of emergence, of pattern rising from chaos. It reveals a truth both scientific and philosophical, that to exist is to deviate, to stray from symmetry, to become more than uniformity allows. In the gentle unevenness of that ancient light, there lies the seed of everything that could one day remember it. Through it, the universe speaks in a language of temperature and wavelength, but the message is emotional in essence. Light, stretched across eons, still carries warmth from a time when the cosmos was young enough to glow. Every sunrise, every flame, every pulse of life is, in a way, that same light reborn, cooled, transformed, but never gone. For nothing truly disappears, it only fades, stretches, and changes form. The light of the Big Bang still fills every corner of space, bathing us in a radiation so constant we no longer notice it. Every second, countless CMB photons pass through every living being, through walls, through oceans, through the very core of Earth itself. The first light moves through us, indifferent and eternal, as if the universe itself were breathing through its creations. In this way, the CMB is not distant. It is immediate. It is the soft background to every moment, the low hum beneath existence. And while telescopes measure it with precision, the meaning it carries transcends measurement. It is the universe remembering itself, the proof that even after billions of years, the memory of creation endures in form and energy. The deeper scientists study this radiation, the more it reveals, not only about the universe, but about the act of looking. To detect it required human patience, precision, and belief in pattern amidst chaos. To interpret it required imagination, the ability to see in noise the possibility of origin. And in that process, humanity mirrored the very thing it studied, emerging from uncertainty, forming structure from randomness, reaching consciousness from energy. The universe, through its creatures, learns to understand itself. The observer and the observed are not separate. They are two phases of the same unfolding. Perhaps this is what makes the cosmic background so haunting. It is not simply the light of what once was. It is the light that allowed everything else to be. Without it, no map of existence could be drawn. Without it, there would be no record, no reference, no memory. It is the baseline of everything, the soft residue of creation that persists when all else fades. In laboratories and observatories across the world, scientists now decode the subtle polarizations and frequency shifts within this radiation. They extract meaning from its microkelvin variations, tracing how matter clumped, how inflation expanded, how gravity sculpted. But beyond the equations, there is something ineffable, a recognition that this faint ancient glow connects all epochs into one continuous thread. A photon released at the dawn of time, now striking a detector on Earth, binds the past to the present in a single act of arrival, and so, the cosmic microwave background becomes both map and metaphor. It charts the early universe, yes, but it also reflects a universal truth about endurance and transformation. Energy never truly dies. It stretches, it cools, it quiets, but it remains. The same could be said of memory, of thought, of consciousness itself. Perhaps what we call remembering is simply the echo of our own creation, the reverberation of the same laws that shaped the first light. In this way, the cosmos teaches subtly that existence itself is an act of persistence against oblivion, that even when entropy pulls everything apart, there remains a trace, faint but indestructible. The CMB is that trace on a cosmic scale. It is the universe whispering that it has never truly forgotten how it began. At the heart of every telescope, every dataset, every equation lies this same wonder, that something as old as time still has something to say. And perhaps, beneath all the technical achievement, that is what humanity seeks most. Not just to measure the universe, but to be remembered by it. To ensure that the story of observation, like the first light, does not vanish into silence. In the end, the faint radiation discovered by accident in a quiet New Jersey field turns out to be a revelation about memory itself, a signal that has traveled through all the ages, through the rise of galaxies, through the awakening of life, through every thought ever formed beneath the stars. It is not just a relic of physics, it is the quiet proof that existence leaves a trace, that the beginning still lingers in the air we breathe. The cosmic microwave background is the faintest memory of all things, the light that never forgot, and through it, the universe continues to remember. Not just how it began, but that it was at all. Even now, across every empty stretch of space, that first whisper moves on, silent, eternal, unbroken. And in listening to it, humanity hears not only the echo of the cosmos, but the echo of itself. There is a sound the universe never stopped making, a silent hymn, a resonance so vast it cannot be truly heard. Only felt through the faintest waves of ancient light, it drifts still, through every reach of darkness, through galaxies now unspooling, through voids so deep that even time hesitates before entering. It is the same whisper that once filled the newborn cosmos. When everything, matter, motion, and meaning, was still one now, billions of years later, it remains, stretched thin but unbroken. the final note of a cosmic overture that began when nothing yet had form, the cosmic microwave background, that fragile afterglow, is not fading into silence. It continues its long, cold journey, unhurried, indifferent, eternal. Each photon carries with it a story written in temperature and time, the pattern of everything that ever was. When the James Webb peers into its reddened depths, when the Simons Observatory tunes its mirrors to the faint hiss of the sky, when supercomputers decode its subtle variations, they are all listening to the same unfinished song, for the universe is not merely expanding, it is composing itself, bar by bar, epoch by epoch, as if creation were not an instant but an ongoing refrain. Hydrogen was its first melody, stars its second verse, and consciousness, perhaps, its brief crescendo, but even symphony's end. Entropy will take its turn as conductor. Stars will dim, matter will fall silent. The expansion will stretch every wavelength beyond the reach of perception, and the ancient radiation will grow colder still, until it no longer warms even memory, yet it will go on. For trillions of years, those same photons will wander through a universe emptied of eyes to see them. They will cross the frozen plains of intergalactic night, brushing against galaxies long extinguished, gliding past the quiet remains of what once was fire and breath and thought in that far future. There will be no instruments left to measure, no telescopes to listen, no minds to interpret, but the light will still exist, unchanged. Unchanged for all the uncounted eons ahead. It will still carry the signature of the first moment when darkness learned to glow. And so the question lingers. Was the universe speaking? Or did it simply happen to sing once, unaware that someday something would awaken to hear it? Perhaps both, perhaps neither. The faint signal is not a message meant for us, yet we found meaning in it anyway. We took the static of creation and turned it into a story, a way of remembering that we too were part of the beginning. Every time an astronomer calibrates a detector to listen for the cosmic background, they are repeating an ancient act, the act of listening to the unknown. And in doing so, humanity itself becomes an instrument, resonating with the same frequencies that once shaped galaxies from silence. It is a fragile connection between the first light and the fleeting minds that learn to understand it. And yet, in that brief awareness, something extraordinary occurred. The universe became self-aware. The cosmos, for a moment, looked inward through the eyes of its own creation. That is the true symmetry of light. Not only that it travels forever outward, but that in our comprehension, it has turned inward, reflecting upon itself in some distant future. When our world is dust and our sun has joined the long procession of dead stars, the background glow will remain. It will not remember us, but it will still contain us, in pattern, in probability, in the quiet arithmetic of existence. The photons that warmed the first atoms are the same that bathe our world today, the same that will outlast it. In them, nothing is truly lost. The past only becomes fainter, stretched across eternity, but never erased, and so the universe continues its silent performance, neither beginning nor ending, only unfolding. A symphony without conductor, without listener, without applause, yet perfectly complete. The faintest memory of all remains everywhere, woven into the fabric of emptiness. It hums beneath every atom, beneath every thought, beneath every breath. It is the cosmic heartbeat still echoing, not through space, but through time itself. And though one day the stars will fall quiet, the light will keep traveling across all that ever was, all that ever will be. A whisper with no destination, an unfinished symphony that plays forever in the dark.